Either all U's, all C's,
No.
or either all U's, all C's, or U's and C's?
Can't be all U's. Remember that the genetic code does not skip any bases.
Would it be 2? Would it be like
Louder.
Would it be 2, like UCU and then CUC?
I'm asking for how many proteins, not how many codons.
3 proteins?
Nope.
It's just 1 protein.
1.
Who said 1? I didn't hear 1. 1. Why 1?
Because all the amino acids will be put together into that one protein. And if there are a couple of various amino acids.
Now, how many different amino acids in the protein? 2. So this, no matter how we break this up, you can't break it up any way other than getting UUU. But if we translate this, what we have is X, Y, back to X, Y. Even if we started synthesis there, we would still have Y, X, Y, X. So this copolymer with 2 nucleotides still gives 1 protein, but it gives 2 amino acids in the protein. They didn't know what they were at the time. That was part of what they were doing. But they saw that it gave a copolymer amino acid of 2 amino acids. Yes?
I was going to ask, how do you know how many letters it makes like in a polymer that makes into a single protein?
Because I gave you the features of the genetic code. Remember, you start at the beginning in a non-overlapping fashion. You use every nucleotide to make a codon. So you had that on Friday.
Right.
Features of the genetic code. There is no other way to do this. You start at the beginning, and you see U, and you translate the next 3 nucleotides, C, C, and so on. Very simple, very straightforward.
I mean, how many codons does it take to make a protein?
That question doesn't, it's not a question. I mean, there's no answer. It just depends on how many nucleotides there are in a message. There is no answer to that question.
What nucleotides can make a protein? How many it takes?
There is no answer to that question. You have to tell me what protein, how many amino acids, and that'll give you how many nucleotides. That question does not register. There's no such question.
So how do you know it's one protein?
Because wherever you start, remember the rules from Friday. You start at the beginning, 3 nucleotides makes a codon, and you go to the next 3 nucleotides, and the next, and you just do that, and you get X for the first thing, you don't know what it is, and then Y, and then X, and then 1. And so the 1 protein then becomes poly XY. You just follow the rules that I gave you on Friday. There's only one answer.
Now with the poly U comma C, there would be more than 1 protein, correct? Because it's not just a random.
Absolutely. With that, because you're not translating a single message, here all the messages are identical. With the other, you're going to have a whole range of different messages. Almost every one is going to be different because it's random. That's why I don't want to go into it. It's really complicated. Then it becomes a statistical problem. Any questions on why it's 1 protein?
Actually, let's say like, how do you know what was like 2 proteins or that?
I don't do what ifs very easily. I mean, it's not 2 proteins, so I have no idea. You can make anything up. It's not one protein with 2 amino acids. You follow the rules from Friday. There is no other answer for this. Yes? Each 3 nucleotide codon codes for 1 single amino acid. That is absolutely correct. Anybody else? With the exam coming up, this stuff is really important.
So it doesn't really matter with this particular simple protein whether you have leucine, serine, leucine, serine, or serine, leucine, serine, leucine.
Very good, that is correct. The reason for that is that I have not yet given you the instructions for how you know where to start. And so that's going to become very important. But this is really what they have. And so the reality is, without the grammar to know where to start, we could start at page 1 or 2 or 3 or 4, but wherever it starts, it'll make you a poly XY, which is equivalent to poly YX. So the biochemists said that these two are equivalent in that it is 1 protein with 2 alternating amino acids. Anybody else? Any questions on that? Let me raise this up. So this is 1, 2, the third one that we're going to do. So the first is a homopolymer with a single nucleotide. Then we did a polymer with 2 nucleotides. Now we're going to look at what happens when we have a polymer made up of 3 nucleotides. So the 3 nucleotides repeats over and over and over again. So this will give, what will it be, UAC, 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 UAC. So again, without the comma, that's a defined sequence polymer. You know exactly what the polymer reads out. Now, we have to figure out how many proteins will this make, and what will each protein look like. So looking at this, again, using the same rules for number 2, where you do not know where it starts, how many different proteins will this repeating trinucleotide polymer make?
1.
There's going to be 1 protein with 3 possible amino acids. And each one of the proteins is going to have just 1 amino acid in it.
Well, that's not 1 protein, then.
That's 3 proteins.
Okay, well, the first one in the reading frame could be UAC, UAC, UAC.
That's
And
1 protein.
That's 1 protein with 1 amino acid.
Yes.
The second reading frame could be ACU, ACU.
That's the second
That's
protein
the second protein with just 1 amino acid.
with 1 amino acid.
And the third protein would be CAU, CAU, CAU.
Okay, so the answer is 3, not 1.
Oh, well, yeah.
Okay, so the answer
Depending on
is 3 different proteins. Each protein has 1 amino acid. So we could translate that UAC, UAC, UAC. So this would be X, 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 or, this is going to get messy, ACU, 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 which would be Y, 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 or we could do CUA, 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 which would be Z, Z, Z. So each of these 3 homopolymers has a very different expression readout, again, going strictly by the rules that we established on Friday. Everybody see, we have 1 protein here, but we have 3 different proteins there. this, again, because I'm giving you the exact message, they didn't know yet at this point what the vocabulary grammar was to start.
So they didn't know the
So,
second one.
so that's going to come later this morning. We will do the grammar for how do you know where to start. And so that's different. This is what you will actually get in the test tube the way they did poly-U. And so there's a really important lesson that will come out of this.
So for number 3, it's 3 possible proteins.
No, it will be 3. I mean, it's not, because the ribosome that makes the proteins doesn't know where to start. It starts randomly.
Oh, this experiment was in vitro. Then.
Oh, absolutely. You can't do this in vivo. All of this is done exactly the way we did poly-U on Friday. So everybody see why the readout is so very different for these 3 very different messages. Any questions? So this is the one that's really very important for the next thing. The fact that you can make a string of nucleotides and without any grammar so far, the fact that you can read out 3 completely different ways using the rules that I gave you on Friday means that you have what are called 3 reading frames. So a reading frame means that wherever the ribosome starts, that's a reading frame. If it starts on the first nucleotide, then we read out the X frame. If it starts on the second nucleotide, we read out the Y frame. If it starts on the third nucleotide, we read out the Z frame. And so we have reading frames. As we look at a gene, now in a gene, we have what is called an ORF. You've seen that terminology on some of the websites. That stands for open reading frame. The operative word here is open. It means that that reading frame only contains codons for amino acids. Remember, we have 61 coding amino acids. And we have 3 non-coding amino acids. We're going to take a close look at that later this morning, soon this morning. So every region that's translated into a protein has 3 potential reading frames, X, Y, and Z. And in a real protein coding gene, only one of those reading frames is open and able to be translated into a protein. The others are closed with stop codons. We're going to see that in a few minutes. Any questions on this? This is the key central part of understanding how genes are expressed into proteins. Yes?
So an open read can both of them lead to 3 proteins in the example we have one.
No, one open reading frame will only lead to one protein in a real situation. The others are theoretical. And because of the double helix, that makes 6 reading frames in this segment, 3 going that way and 3 on the other strand. Anybody else? An open reading frame contains Anybody else? Okay, so let's do an in-class cooperative learning exercise, and we'll see how this stuff really works. So now, before you start, the easiest way to do this is to take the sequence at the top, so that's a nucleotide sequence, and divide it into codons. So start with the first, put a line through it between the two G's, and just put a line through every 3 nucleotides. And then where it says, what are the first 10 amino acids, write the amino acids above the DNA sequence. Don't put the amino acids in the space below. It will be easier to solve the problem if you write the amino acids directly above their codon. And then what you have now is the code dictionary, the standard code dictionary. Use that to answer the questions.
He wants us to write this and just write.
Yes.
Or does he want us to also do like UGG and then the other? Does he want us to do it all 3 ways like that third one or no?
No.
Okay. And then when you said open reading frame only makes amino acids, is he just saying that there's no protein that pops out? It just keeps throwing out amino acids because there's no stop.
An open reading frame is the reading frame that allows for an environment to be coded so that it's actually able to code. So let's say that we started there. That's not the open reading frame since it doesn't start with methionine, and it has to start with methionine to go.
Okay. Bless you, bless you.
Yeah, I know. We were wondering. Methionine.
Amino acids. We're writing this out. So for the first one, since there's no defining, there's no start.
Right.
And then this one, no changes. It comes back to the same thing. This one just ends like it's a stop. This one is okay, it just changes something. But this one is a frame shift, and this one there's also. Should we say frame shift or just rewrite this?
At this point, explaining it would be sufficient. You don't have to rewrite the entire code.
If we wrote frame shift, would be like, if we had the same question on the test, it's like frame shift, would you just be like 12 points off?
No, because he's about to explain that.
Okay.
Yeah, he just hasn't explained it yet.
As long as we know what it is, it's okay. Because one's a frame shift with deletion, one's a frame shift with insertion.
Yeah.
Okay.
This one where if the A was changed to a G, I would have to rewrite the whole sequence, but would it be a G instead of an A?
You don't have to rewrite the whole sequence, just rewrite what is changing. So the only thing that's changing is that.
You said that was the ABC was changed to AE.
Right. Is there something else that's special about AUG? Right. So if you no longer have to start code on,
It would start over here. Wait, are you?
yeah, no, that I'm indicating it would start.
Yeah.
And that's something that you should write.
Oh, okay.
So if there's no start, it can just sort of like pick randomly and just like, boom, start.
I mean, usually, no, it doesn't randomly. It has to find another AUG to start.
So it just, for this sequence, it would just keep going until it found it. Okay. So all this would be gone, and this could be like the important part, like makes it full left instead of.
Right. Or whatever, yeah.
So that's the starting point. So if this one was just you have to find each AUG.
Orange hair is something. It tastes like orange.
But it sounds terrible. Oranges and
Do you remember looking at like a smoothie with vegetables? Yeah. I hate carrots plain. I can't help it. But like, I just like take carrots and spinach and throw it in a blender and this weird. I can't taste it.
It's so strange to me.
It's really good. Like, seriously, go try it.
I'm saying it. I'm sure it's good. But that's a weird combo.
Well, here's the thing. You have to make sure that your spinach is
It looks like food.
like really make sure your spinach is like blended though, because like you'll get like certain.
So basically, vegans and vegetarians.
No,
Everyone should.
that's how I eat carrots. I'm like a vegan. Like if you do like pureed carrots and tomatoes.
I don't really eat carrots.
Yeah, I don't know. I eat broccoli. So I have like no beta carotene, so I should have glasses.
I like my leafy greens.
You know what's fun? I had to stop the video because I've had 2 minutes stuff now because I was like, I forgot to erase the last one. I don't know. 2 gigs left. 5 minutes are coming up, so it's like.
I thought the whole class was
Okay, so let's talk about what we have just done. First of all, for the last 2 are complex changes. They look really simple, but they follow from this concept of a reading frame. When you put in a nucleotide or take out a nucleotide, you are changing the reading frame. Now, some of you wrote down stop, but stop is not an amino acid. So let's be very, very clear on this. When you do any translation on the second exam, if you write stop or a stop codon, you will lose points. And so it's asking you what is the amino acid or what is the polypeptide that's being made. Stop is not an amino acid. Stop is a command. It says stop. And that's exactly what happens on the ribosome. It's a command to the ribosome. So now let's go through these, because we have a whole bunch of different kinds of amino acid changes. Yeah,
So what do you put?
I can't hear you.
What do you put instead of stop?
Nothing.
Just
It says stop writing, so you don't put anything. The last amino acid is the last coding codon. Don't put anything for a stop codon. Someone else had a hand up?
So you won't write the codon that codes for stop?
That is correct. It will not, the codon doesn't, it's asking for what does it code for. And a codon that codes for stop is a command. It doesn't code for an amino acid. So be very, very clear on that. Yes.
So more or less for D, you just put like .12 and that's it.
I'm not asking you to do dot, dot, dot. It just says proline is the last amino acid coded by that chain.
Got it.
So number B, rather, the first one that you look at, where you change from A to a G. You've changed a methionine codon to a valine codon. That's called a sense mutation. Sense means that it has changed from one amino acid to a different amino acid. C has no change. That is a silent mutation. So a mutation, as we will see in the next chapter, a mutation is any change in the DNA. So what we're looking at are a whole series of different kinds of mutations, the effect of different kinds of mutations on the readout of an open reading frame. And so the change in C is a real mutation that changed the DNA sequence but did not change the amino acid. So D now changed an amino acid codon to a codon that does not code for an amino acid. That's a stop codon. That's a command. You don't write commands as part of the readout of an open reading frame. So this is a nonsense mutation. So a sense mutation changes a codon to a different coding codon. A nonsense mutation changes a codon to a stop codon. E is another sense mutation. F and G are really special. This goes back to the 3 different reading frames. So what you're looking at when you take out or put in a nucleotide is going from the YY frame to either the XX or ZZ, depending on where it is. And so that's a special kind of mutation called a frame shift. Very descriptive names. The name is telling you exactly what is going on. So a frame shift mutation says that this is a mutation that takes you from reading frame number 1 to reading frame number 2 or number 3. And so as you saw, when you wrote out change, the consequence to that, it's pretty severe. It doesn't just change a single amino acid, but changes everything after that frame shift. You have completely different amino acids until you hit a stop codon. And then, oh, you erase this again. And then, because you're in this open reading frame, a frame shift that comes out early is going to make a very short protein, whereas a frame shift that comes out late might make the same protein. But the point is, from the point of taking out or putting in a base, everything changes. And because in real genes and real proteins, you have one open reading frame and two reading frames that are not open, two closed reading frames. Any questions on this whole set of different kinds of mutations?
The nonsense mutation, is that only when it changes to a stop?
By definition, a nonsense mutation is a change from a coding codon to a stop codon. And you do not write stop. That will cost you points.
Should these questions appear on the test, do you want us to write the entire sequence out, inserting change?
You should write out exactly what the question is asking. Nowhere does it say write out everything except for the original on the top.
Okay, so
all
the change
all you're asked to do is write the change that occurs. Make a methionine to valine, for example.
So on D, when it changed it to a stop codon, don't write stop, right?
Well, it depends on how the question's worded.
Okay.
So if you're writing out a protein, then you just stop. If it says what is the codon, then it's a stop codon.
What happened, so in B,
In which?
in B, the very first codon was methionine, which was the initiator.
Ah, but I didn't tell you that yet. So that's the last thing we're going to do. And so that's part of the external punctuation. Remember, there's no internal punctuation. We have external punctuation only. So in a real gene, we have three different ways to read out that message and read out that information. So we now have a definition for an open reading frame is AUG, which is the start, as I pointed out, to stop. And so you have on your dictionary in front of you, there are three different stop codons. Remember what we did on Friday, 61 coding codons and 3 non-coding. So the definition of an open reading frame is from a start codon, which is AUG, to a stop codon, any one of the 3 codons. Any questions on that? We're going to come back and take one more look at that. Remember, we went through the features of the genetic code. And so, number 7 was we have an ordered code. Now that you have the code dictionary in front of you, you can see what an ordered code means. That means, first of all, codons for an amino acid are grouped. So just look at the dictionary on the bottom. UUU, that's the first one that we did on Friday. UUU codes for phenylalanine. There are 2 codons for phenylalanine, UUU and UUC. Those 2 codons are grouped together. So that's part of what an ordered code means. And you look down the line, leucine is more common in amino acids and proteins, and so there are more leucine codons in phenylalanine. All 6 leucine codons are grouped together in this dictionary, and you just go down the line and across the page, and you see almost every single amino acid, those codons are grouped together. I think there's only one exception to that, where there's a couple of codons split off. And so the first part, it's a two-part definition. The first part is our ordered code. Codons from amino acid are grouped together. Second part, codons for similar amino acids tend to be grouped. So look at that code dictionary. That first column on the left, phenylalanine, leucine, isoleucine, methionine. Those are all similar amino acids in that they are hydrophobic amino acids. Hydrophobic means these amino acids share a common biochemical property. They do not like water. And so all of these hydrophobic amino acids tend to be grouped together by the middle base. Phenylalanine, leucine, isoleucine, valine, they all have U in the middle position of the codon. Does everybody see that? Look at that third column. The third column has A in the middle. If you've had some biochemistry, you see that all of those amino acids, tyrosine, histidine, glutamine, asparagine, lysine, aspartic acid, glutamic acid, those are hydrophilic amino acids. Hydrophilic amino acids means that those amino acids like to be in water. And so that's part of the folding process. As proteins fold up, especially globular proteins, it folds up in water automatically to put the hydrophobic amino acids inside and the hydrophilic amino acids on the outside. That's part of what we discussed on Friday, why so many proteins fold up automatically. It's the way they're assembled from regions with hydrophobic and hydrophilic amino acids. Does everybody understand what I mean by ordered code? So a consequence of an ordered code is that minimizes lethality. It's not part of the definition. It's just a consequence. What do I mean by minimizes lethality? Let's say we have a mutation in a UUU codon, a mutation that changes it to UUC. Well, UUU codes for phenylalanine, UUC codes for phenylalanine. We have a very definite mutation, but no change in the amino acid, a silent mutation. So you can't get a mutation, you can't change the amino acid because so many of the mutations are in the ordered codons with a consequence that we go from one codon for that amino acid to another codon for that amino acid. So that's one part. Let's say we go from UUU to CUU. If we have a mutation, so this is a mutation, this is a mutation, so this will change the amino acid. Definitely. It's a sense mutation. But we're going from phenylalanine down to leucine. We are replacing a hydrophobic amino acid with just a different hydrophobic amino acid. Now there's a chance that it might change the function of the protein, but there's a better chance most of these mutations like this will have no effect on the phenotype. And so let me read you something. 30% of all mutations result in no change at all. That is, just make random mutations throughout the code dictionary. No change at all. Another 25% result in a minimal change going from a hydrophobic to a hydrophobic or a hydrophilic to a hydrophilic. That means about half or slightly more than half of all your random mutations that occur are going to have little or no effect on the phenotype. That's pretty important. So in the age of computers, people could make millions of different code dictionaries. So this is just one possible way to organize 61 coding codons. People have done that. They've written programs that computer generate all possible code dictionaries and then check, again, very easy by computer, check to see which dictionary is best at minimizing change, serious change in amino acids. And maybe surprisingly, maybe not surprisingly, your code dictionary is the best at minimizing mutational lethality. That means minimizing the chance of having a serious amino acid change rather than a hydrophobic to hydrophobic change. There are other dictionaries that are equally good, but in the millions of possible arrangements for a codon dictionary, yours is the best. No one ranks above it. Others are equal, but there is no better code dictionary. Yes?
Is that us like humans or us like mammals?
Well, so you have the same code dictionary that E. coli does.
Okay.
You and the saguaro cactus have the same code dictionary, you and E. coli. So that dictionary that you now have, that's in your book also, that's the universal dictionary for all cellular organisms. I told you, the code dictionary is universal. So the major exceptions are mitochondria and chloroplasts. And they're just a simplification. We're not going to go into what that means. But they're just an easier code for the ribosome to read out. Anybody else? Any last questions on this? Okay, so still on features of the genetic code. So this is just an extension of what we did on Friday. So remember, somewhere up on top of the list that we did on Friday for features of the genetic code, I told you that there is no internal punctuation. Once you start reading, you read every single nucleotide. But that's just once you start reading. External punctuation, now as a lot of you already know anyway, that tells you where to start and where to stop. So the external punctuation is AUG, codes for methionine, and that is the start. So this happened to start with AUG. And so the reality is if you change that to valine, you wouldn't be able, in real life, you wouldn't be able to read that out. But it's still a sense mutation that changes from one amino acid to the next. So we have start, and we have three mutations, three codons rather, UAA, UAG, and UGA, code for stop. Stop is written with 4 letters. It is not an amino acid. Stop is a command. Stop tells the ribosome, let me bring this down again for a second. In the X frame, only, now with the stop codon, it just says read out and put 1, 2, 3, 4 X amino acids and then stop. There are no amino acids for any of the 3 stop codons. It is a command to tell the factory, the ribosome, to stop synthesis. So when you see that, when you're translating anything, whether it's homework or exam, if there's a stop codon in frame, you just stop writing. Don't put anything down. But remember, the definition of that reading frame is in a real protein, one is open and the other 2 are going to have multiple stop codons. That's the reality of real protein coding genes.
Is it possible to have UAG multiple times in it before stop?
Out of frame or in frame?
In frame.
No, because UAG is a stop. So as soon as the
AUG.
Oh, absolutely. Oh, yeah. So that's a good point. So AUG is the start codon, but methionine also comes up inside proteins. And so AUG inside the reading frame just codes for another methionine. Now that's absolutely possible, but not stop. In a real protein coding gene, there'll be one stop in the reading frame you're looking at the end, and that's the end. But multiple stop codons in the other 2 reading frames. Any questions on that? This is the end of the material for exam 1. Thank you. Exam 2. I have to listen to myself sometimes. Remember, the exam is Friday. Again, I will put up last year's exam in the copy center, but after Wednesday's class. Just too much to get over there in the morning. It'll be in the afternoon, and we will have help sessions throughout Thursday. Any last questions on the genetic code before we move on to section 3, exam 3 material?
If you had a question on the test that was like F or G, would you want to just write frame shift or frame shift because of a deletion or frame shift because of an insertion?
Well, no. So if it's worded exactly like F and G, then you put down all the changed amino acids until you come to a stop, and then you stop writing. That's the way it works.
All right.
Do you write the amino acid that changes or what it changes into?
No. So the question asks, what sequence change will result? When you write the new amino acid sequence, or the new amino acid sequence will end with a stop codon, you do not write a stop at the end. Anybody else?
So, if the question were to ask, what sequence change would result? Are we to write the whole sequence, or just part of the sequence that changes?
Just the part that changes. That's what this calls. Yes. Robert.
If we reach a stop codon and we're writing out a sequence, what about the codon that just not write this down at all?
Right. So in a real gene, it just goes on millions and millions of bases. But the ribosome is reading a copy of 1 second, and even that has nucleotides after the stop codon. We're going to see that in the coming chapters. So you stop writing when you hit a stop codon in frame. Anybody else? Okay, so the first chapter on the third section of material is mutations. But we've been playing with mutations today. Remember when we discussed the Watson-Crick model for the double helix? I said there were really important questions in 1952 when Hershey and Chase showed that DNA was the genetic material. People had to completely change their way of thinking. And so the important questions were, how is DNA faithfully replicated? We've done that. Now they have to think about, how is information for a protein encoded in nucleic acid? We just finished that. And the third important question is, what is a mutation? People had no idea. You've grown up in this modern molecular biology age, which is second nature to you. Try to put yourself in the position in the 1950s. People had no idea, but people knew about mutations. They're in the Bible. And so mutations, called sports back then, were very well known to everybody. So we're going to talk about mutations, but we're going to talk about not all kinds of mutations. Basically, we have a new definition for mutation. The old definition, pre-modern biology, was a change in the genotype, Mendelian terms, that changes the phenotype. But now that we have DNA sequence, and we can get DNA sequence relatively easily, there is a new definition of a mutation. And that's any change to the DNA. It's really a simple definition. Any change whatsoever. So on that board behind the top one, you have a whole bunch of different kinds of mutations. That's primarily what we're going to be focusing on. So mutation also encompasses polyploids and aneuploids. Mutation certainly encompasses translocations and inversions. Those are changes to the DNA. But in this chapter, we are just going to look at what has commonly been called micromutations. So micromutation, micro is small, so we are going to focus, for the most part, with one exception, on mutations that typically involve a single base change. In other words, basically what we just did in class this morning. So we can look at this in terms of the DNA. We have an AT base pair, can change to PA, can change to CG, can change to GC. And so we have different kinds of changes. Remember now, this is AT base pairs. So we can change an AT, for example, to a GC. So this is a transition mutation. A transition mutation is a change from a purine to purine, or pyrimidine to pyrimidine. In other words, what we changed here, A purine to G purine. That's called a transition mutation. On the other hand, we have another kind of mutation, a transversion change from purine to pyrimidine and or back. So two very different kinds of changes. All of the ones on the outside are transversion mutations. So A, the purine A changes to the pyrimidine T, AT to TA. We swap these, that's a real mutation. Remember, we're reading out one strand, that changes the sequence. That's a transversion. All the changes on the inside, A, P to GC, TA to CG, these are transition mutations. Everybody see the difference between the two? So let's look at what is a transition mutation. I haven't been drawing it, but there really is a hydrogen here. And this hydrogen is free to wander back and forth. And so if it wanders up, if this hydrogen wanders up to that O, it's going to take out the double bond and make it OH. And so this is T in the common form. This is T in the rare form. This is called a tautomeric shift. That hydrogen not that one. That hydrogen can wander back and forth. It's a consequence of a ring-based compound. So tautomeric shift gives rise to transition mutation. The consequence, T in the common form, you all know pairs with A. The definition of a transition mutation, T in the rare form pairs with, and properly pairs with the other purine. So we still maintain purine pyrimidine base pairing. So that's a transition mutation. A transversion mutation we rotate this bond, rotate that bond that connects the base to the sugar, we're putting this face that ought to be hydrogen bonding with A, we're putting this face back and bringing that CH3 out. This is the cause of transversion. This is rotation around the glycoside bond. You had a question?
Yeah, so I just want to read what that says up there with the transition mutations at CH3 to CH2.
What?
For the TC to TR.
No. CH3 doesn't change. Yes.
When the T rare pairs with the G, does that change the amount of hydrogen bonds, or it's just they stick together?
It's going to be hydrogen bonds, but a different set of hydrogen bonds. And so this is the proper base pairing with an OH there and the hydrogen bond from there. Now, common and rare really means that. It means that this hydrogen wanders back and forth. The vast majority of time, it's in this position, the normal position. But rarely it can be up there. If it happens to be caught during replication, during this automeric shift, the polymerase will look at this and say, oh, the correct structure is to put a G in there. The polymerase is not making a mistake. This is a consequence of this vibration around a ring compound. The same is true for this rotation. If we rotate it, then T is going to pair with a base that is not A. And so these rotations, these quantumeric shifts, this is all about natural, spontaneous mutations. Every minute that you're sitting here, every minute that you're alive, this is going on automatically in your cell. Any questions about this?
Right, I said one rotation around the lysate bond.
Glycoside bond?
Do transition and transversion occur in the double helix where they are bonded?
Even there, no. All of these happen all the time spontaneously. When you come back on Wednesday, we'll continue to explore